Hello CityJS conference, and thanks for having me. A bit about me to begin with. My name is Patrick Kunka and I'm a principal software engineer at DAZN, which is a global sports streaming platform with our head offices here in London. My background is in JavaScript and front-end web development. I've spent the last 6 years or so specializing in video playback on the web. And in this talk, I'm going to be speaking about how we're developing and testing video players at DAZN using in-house JavaScript-based network simulation tooling. So you may already have some idea of how a modern video player works, simply through observation. When you're watching your favorite streaming service, you might have seen things like an initial 10 seconds or so of visibly compressed, low-quality video, like this picture on the left, before the player then jumps up to something more high definition. And this behavior is what we call Adaptive Bitrate, or ABR video. And the scenario I just described is not entirely necessary and can be mitigated, but it's a good way to quickly illustrate the fundamentals. An ABR player has many different video and audio quality levels available to it. Each quality level is encoded at a different bitrate, which means the amount of data that is used to represent 1 second of video and audio. And this is a function of compression, resolution, and frame rate combined. Within each quality level, the video and audio is then broken up into small files or segments, each one typically only a few seconds long. And this means that the file size for a segment of 2 seconds of video can vary from a few hundred kilobytes at the lowest bitrate all the way up to a couple of megabytes for the highest bitrate. And between these, there may be 10 or more quality profiles for the player to choose from at any point in time. The choice of bitrates and chronologically ordered segments, which are provided to the player via a text-based manifest file, which is essentially a structured list of URLs, gives the player the ability to smoothly navigate varied and changing network conditions and pick the most appropriate quality profile available for the customer's internet connection at any time. So if we could visualize a player's bandwidth estimation and its choice of quality profile, we would see something like this chart, showing the player gradually stepping down through quality profiles as the bandwidth deteriorates. So generally speaking, an ABR player has 4 primary goals. Firstly, start up quickly. Secondly, maintain the highest quality possible given the current estimated bandwidth. Thirdly, avoid rebuffering. And finally, recover from failures. So the interesting part for me about working in the field of video player development is that these first 3 goals are actually often conflicting. So in order to create a great customer experience, we must develop models and algorithms that understand how to make the correct trade-offs and sacrifices, and also take the best decisions at the right moments. If our estimates are inaccurate, or if we react too late, then the customer is likely to experience rebuffering mid-playback. It's a process that's highly asynchronous in nature and one that has to reliably function across a huge range of network conditions. Thanks to modern web standards such as HTML, video, and the newer Media Source Extensions API, this logic can now live entirely in JavaScript, which is how I became involved in this area. In order, therefore, to build reliable, testable behavior in our video players, we need ways to deterministically simulate every aspect of a real customer's internet connection and assert that a player behaves as expected every time. So you'll most likely be familiar with network throttling options such as Chrome DevTools or software like Child's Proxy. Perhaps you've even experimented with the low-level Linux traffic control protocol. All of these are highly valid and valuable and often very powerful tools, but many have shortcomings when it comes to creating a holistic playback testing stack. So in this presentation, I'm going to talk about how my team at DAZN built our own network emulation testing tool using TypeScript and Deno that can be run locally on any laptop or remotely in the cloud via a CI pipeline. So firstly, why did we want to do that? Well, we wanted something that was platform agnostic to begin with. Chrome's throttling options are great, but not much use if we want to test playback in Safari or on a smart TV with an OEM embedded browser. Secondly, we wanted something that could run either on our local machines during development for testing or just hacking around with new ideas, but also remotely via a continuous integration pipeline and at scale, ideally running hundreds of simulations in parallel as quickly as possible. Finally, we wanted to democratize the tool and encourage contribution from across the team. The DAZN playback team is primarily a team of JavaScript and web front-end specialists, so anything requiring physical hardware, complex setup, or low-level native code was to be avoided to prevent a reluctance with uptake and contribution that we'd encountered in the past. So what did we want our tool to do? One of the most important goals of the project, as I mentioned earlier, was to create something as close to deterministic as possible. So when we test using Chrome DevTools or Charles Proxy, we typically use to test against specialized test content downloaded from a real CDN on the internet. These tests are useful, but they can be unreliable because they're susceptible to influence from external processes, such as sudden changes in network conditions due to competing traffic on the same network, or a background system software update kicking off in the middle of a test. So we realized that if we could remove the internet from the equation completely, we should in theory be able to run the same test over and over with the same results. Another goal was to be as granular as possible in what the simulation could affect. Reliable bandwidth simulation, or throttling, is probably the most important and most obvious feature of such a tool. But we wanted a tool that could also do a lot more and really simulate anything that the real world could throw at us. And I've got a few examples listed down here. Finally, we wanted a tool that was effortless to use by testers and software engineers alike. So controlled either by very easy to build no-code JSON test files, or manually via a simple UI. And as easy as possible to develop for and to add features to, meaning a familiar stack and tooling for JavaScript developers. So let's take a look at the stack. You'll most likely be familiar with most of the software shown here, so I'm going to be focusing on those probably least familiar to front-end developers, those being Dino and the JavaScript Streams API. But I'll talk a bit about how we're using containers first. So Docker Compose, or Amazon ECS, are container orchestration tools which facilitate the running of multiple Docker containers or services and enable communication between them via a virtual network. You can hopefully already see where this is going. So the initial concept was that by using Docker Compose locally or Amazon ECS in the cloud, we could create different services with very specific goals and have them talk to each other in a way that would mimic a client, a player, if you will, talking to a CDN with the internet in between. Dino was something that I added to the project fairly recently, replacing a lot of node.js code in the process. If you haven't heard of it before, Dino is a new TypeScript native server-side runtime from Ryan Dahl, the original creator of node.js. And amongst many other great features, it comes with a powerful standard library that actually contained almost everything we needed for this project out of the box without having to import any third-party modules. Another great feature for this project is its optimized approach to handling back pressure in streams, which we'll come to later on. So let's start with a high-level view of the architecture. Within our virtual local network, we have a number of services communicating via HTTP. Firstly, on the left, we have our player under test. It exists within an HTML test harness loaded into a headless browser and driven by Selenium and a custom JavaScript instrumentation layer, which essentially controls the player, calling play, pause, seek, rewind, other public API methods, and at the same time collects metrics back. So this service is known as the runner, and it's also responsible for orchestrating tests and returning a final pass or fail based on evaluation of the events and metrics collected from the player during the test. On the right over here, we have our file server, which is a simple static file server with access to a mounted volume containing our video and audio segments and manifests. Given the huge choice of technology that Docker facilitates, we really could have used anything for this, such as a single line of Python, but we opted for Dino's standard library HTTP server with the aim of a TypeScript everywhere approach. The proxy service in the middle, again built with Dino, sits between the player and the file server and can be thought of as another HTTP server, routing all requests from the player straight through to the file server while throttling throughput or affecting network behavior in some way as data is streamed through it. I'll be taking you through the implementation here in some detail later on, but suffice to say, having our bandwidth throttling code sit within a TypeScript-based HTTP server made it pretty trivial to extend the tool with other features like latency simulation and error simulation later on. So let's take a look at the request lifecycle of an HTTP request coming from the player. Within our Docker Compose or ECS network, each service has its own address or port on localhost. For example, the file server could be located at port 3000 and the proxy could be located at port 4000. In other words, any file on the file server will be available at the same path name on either port, but the behavior of how that request is fulfilled will be different. So when a request is made via the proxy, we simply need to add the intermediate step of a server-side fetch request from the proxy to the file server, shown here with the dotted line, and stream the response directly back into the pending client requests from the player. We now have everything in place to begin plugging in our network simulation code. So how do we build a bandwidth throttle in JavaScript? Firstly, our throttle must sit within the proxy and ensure that the speed at which packets can flow out of it is rate limited, and any chunks of data arriving from the file server faster than that rate are buffered up in memory and then released at a steady constant rate. So this is where we get into the JavaScript Streams API. A stream in Dino, Node.js, and modern browsers is an interface for dealing with asynchronous data transfer, typically large amounts of data. The most common examples would be I/O, reading or writing to disk, and network requests. A stream allows us to break up a large resource, such as a network request or file read, into small chunks of binary data, and handle and process them one by one, rather than having to wait for all data to arrive before processing it monolithically. This allows for granular, immediate, and regular data processing and is much more memory efficient, particularly in the case of large files, as memory allocation in the JavaScript layer is kept to a minimum. The Streams API should not be confused with streaming video or RxJS observable streams. Streams are simply chainable API services which can be piped together to efficiently move binary data between inputs and outputs. I've got a couple of API examples here. So in the first one, data is streamed from a readable input stream into a writable output stream using the readable stream's pipe2 method, which is a means of connecting multiple stream implementations together. Once all data has been written, the returned promise is resolved. In the second example, we chain in an additional processing step using the pipe-through method, which returns another readable stream, which can again be piped into a writable output. The distinction here between pipe-to and pipe-through is necessary due to the fact that one is final and returns a promise, while the other is chainable and returns another stream. So let's take a look at what our throttle will look like implemented with the Streams API. Firstly, the What Working Group Streams API standard defines three types of streams. Firstly, readable streams, streams from which data can be read, writable streams, streams to which data can be written, and transform streams, which are both writable and readable and which can manipulate the data passed through them. It's worth noting here that Node.js also implements a very similar but older and non-standard version of the above, which you'll probably be familiar with if you've ever worked with server-side JavaScript before. So in the case of our Dino proxy, the server-side HTTP request gives us a readable stream, and the client HTTP response gives us a writable stream. Our throttle will sit between these two existing streams, making it both writable and readable, and will be implemented therefore as a transformed stream. One of the many brilliant design decisions taken by the Dino team was their decision to implement standards-based web APIs wherever possible over proprietary ones. Because of this, we get native access to things like Fetch and the Streams API on the server for free. So as per the Streams API standard, Dino exposes a transform stream constructor in the global namespace that we can instantiate with custom transform and flush callbacks in which our throttle's business logic can be implemented. So firstly, the transform callback is invoked by the platform whenever an individual chunk of data arrives from the underlying readable input stream, giving us the ability to process or manipulate that data in some way. The platform will only send more data once we signal that we're done with the transform step. This is achieved either by instantly returning void, which would be synchronous processing, or returning a promise which is resolved after processing is complete, which would be asynchronous processing, and that's what I've shown in this example here. The amount of data contained within a chunk is arbitrary and arrives as a typed array of binary data that can be iterated over and processed as needed. So via these two callbacks, the platform also provides us with a reference to a controller object, which is really just an API surface which we can write our output to once we're done processing, using the controller's enqueue method. Once all incoming data has been pushed into the transform stream by the platform, the flush callback will be invoked. And this gives our implementation the opportunity to tell the platform to wait until we've finished processing and any cleanup steps before destroying the stream and releasing memory. We do this again by returning a promise and resolving it when we're done. In the case of our throttle, we don't actually want to limit the rate at which data is written into the throttle, only the rate that it is read out. Therefore, all transform callbacks will need to behave synchronously and return immediately. As incoming data builds up in the throttle's internal buffer, we'll use a simple timer to push data back out to a reader at a configurable maximum rate via the enqueue method. It's worth noting that during this time, data will be accumulating within the JavaScript memory, known as back pressure, where data is coming in faster than we can push it out. And it must be handled carefully to avoid performance bottlenecks. JavaScript's typed arrays can help here, giving us efficient write and read access to pre-allocated raw memory. So let's take a quick look at a simplified implementation of a throttle implemented as a transform stream. We have on the left here a factory function, createThrottle, which returns an implementation of a transform stream. Firstly, we have some parameters, a content length parameter, which is the number of bytes which we expect our request to be. And we're going to use that to allocate all necessary raw memory up front. And we also have a couple of optional parameters which are going to define basically what our throttling rate is. And that's done as a combination of the processing interval, which is how frequently we want to write data out of the proxy, and the number of bytes per interval to be pushed out, which is basically the rate. And you can see that defaults to infinity, meaning that by default, no throttling is applied. Data is just going to be allowed through unlimited. So then we set up a few variables, our buffer, which is probably the most important thing, where we're going to store the data that's building up. And we're going to use a typed array for that. And the content length parameter, again, we're using that to define how much memory we want to allocate. We have a deferred promise called done, which is going to allow us to affect the control flow of that flush callback outside of the callback. We have a reference to the controller, which we're going to hoist the controller into later. And then we have a couple of indexes, which are going to allow us to keep track of where we're writing to the buffer and when we're reading from it. The second most important thing of this implementation is probably the processing loop. And I've extracted the process function out to the right there so that we can focus on it individually. But essentially, we have an interval, a timer there that's running at that process interval, and it's calling that process function every time. We then have the transform callback, which is we're going to use that to receive chunks and push them into the buffer. And it also gives us access to that controller reference, which we're going to hoist into the parent scope. And each time we push data into the buffer, we increment the write index to make sure that the next chunk is written into the right place. Finally, we have our flush function. And as I mentioned before, we're using that deferred promise there to just have the platform wait until all data has been pushed out before we return. And once that happens, we also clear the interval and stop that timer. Finally, we return the implementation of the transform stream with the callbacks provided. So looking at the process function now on the right, the first thing we want to do is check whether all data has been written or processed. If it has, we can resolve the deferred promise and end. Otherwise, we need to take a chunk out of the buffer based on the defined rate, the bytes per interval. So we use the start read index and then we create an end read index using that bytes per interval. We take that chunk and then we push it out using the enqueue method, and again incrementing that read index so that the next read is taken from the correct position. So we can now take a look at how the throttle would fit into the lifecycle of an incoming HTTP request in our Deno proxy. The first thing to note is how minimalist the API of Deno's standard library server is. The server instance is implemented as an async iterable, meaning that incoming requests can be handled without having to add a single event listener or callback, which is really nice. We firstly take the URL of our incoming request and redirect it to the file server. We then kick off a server-side fetch request, which gives us access to that readable body stream, and also headers and a status code if we want to forward them back to the client. Using that content length header, we get that content length in bytes, which we're going to use to create our throttle for the request and allocate that raw memory. We can then basically pipe the body from the fetch request through the throttle and out into a reader. And the reader is just an interface that allows us to provide that stream back to the request response method, which we can see at the bottom here. So we'll respond to the request with the throttle reader, which is the stream, and we're forwarding on the status code and the headers. So that's a pretty simple implementation. It works well for consecutive non-overlapping requests, but in order to accurately simulate the real world where a client might actually make multiple overlapping HTTP requests in parallel, and we need to therefore correctly distribute the bandwidth between them all, quite a lot of additional complexity is required. And there's obviously many other edge cases and gotchas too that have to be accounted for. So I actually ended up open sourcing the final throttling library, and it can be found at GitHub at patrickkunka/bandwidth throttle stream. And it's actually compatible with Deno and node.js, which was quite an interesting challenge to build a library that could work in both, but that's something for another talk. So time for a demo, and let's take a look at the final tool in use. So What we're looking at here is basically the UI, which we're going to use to configure the proxy. I've got a throttle set up here, and it's set to 6 megabits per second of throughput. I can also add some random jitter to that, again, kind of creating more of an element of the real world rather than the sort of lab conditions. So basically it will randomly fluctuate 50% plus and minus above 6 megabits if I added that. I can add latency, so basically simulate a CDN that's really far away, stick 400 milliseconds of latency in front of every request. A couple of other things you'll notice on these is we've got this pattern matching field. So for example, if I wanted to add latency only to MP4 files or only to dash manifests, I could do that very easily. A few other options we've got here is the ability to have specific requests fail with a 404. This is really useful, especially combined with this percentage. So I can set that down to 10%, and that will basically mean that 1 in 10 requests, let's say, to a manifest file are going to fail with a 404. And this just allows us to really build out and test behavior like retries and other sort of resilience measures that we have to have in players to keep playback going at all times. Finally, we have this hang behavior as well, which just simulates that CDN under load where it just doesn't respond to the client request and just leaves it open, which allows us to build behavior like cancel and retry. So if I just clean this up and we'll go back to our throttle to begin with, I'm going to open up these metrics on the right, which we're going to look at in a second. In this next tab here, I have the player under test. So this is just a very basic test harness. I have a HTML5 video element here with my custom JavaScript player kind of instantiated over the top. I've got a link here to a manifest, which is sitting on my file server behind the proxy. If I initialize that and just start that video going, we can see the test video playing. I'm now going to go back to the controls, and we can see some data here coming through. So the player is playing, there's some HTTP requests being made, and the player has a bandwidth estimate of around 6 megabits per second, which is exactly what we have configured it to. So just to kind of demonstrate again, we can add some latency here, and we should be able to see that coming through in this gray section on this chart here, the waiting time there for around 400 milliseconds per request. And we can reduce the throughput and see how the player reacts to that as well. So what we'll see is the bandwidth estimation dropping down, and the active bitrate here, which is basically the chosen quality profile, will be reduced as needed. So this is looking quite a lot like that diagram that I showed you at the beginning of the talk. So let's go back and stop this test. What we've been looking at just there is me using the tool through the manual UI, but a lot of what I talked about earlier was how we can use this to automate tests. So we also have this JSON format here, and this network periods section is basically a data model that describes everything that I was just doing on the UI, but over time. So I can say that I want a test that runs for 30 seconds, and for, from 0 seconds up to 15 seconds, I'm going to have 6 megabits per second of throughput through a throttle behavior, and then I'm going to drop it down to 3 megabits per second. And I can add latency and error requests and any other behavior that's available through this syntax. And then I can use test periods here to basically evaluate whether the player has behaved as expected over that time. So in this case, I'm looking at that 15 to 30 second period after the bandwidth has been reduced, and I'm checking that the player adapted, which is a term that basically means that it changed quality level. And I've got a syntax here that say, okay, it must have adapted at least once and no more than 2 times. So that kind of gives you an idea of, how we would build our automated test scenarios, and those would be typically run as part of our CI pipeline. So I'm just going to return to the deck. I guess another thing worth mentioning is that everything we've looked at so far has really been in relation to video playback, but you may already be thinking that the ability to automatically drive any HTML page through simulated network conditions could be just as beneficial for applications in general. So for example, being able to programmatically test image loading failover behavior or retries on a failing API endpoint could be really useful, and to be able to do that all in a kind of declarative scriptable fashion. So that's something we haven't really investigated yet. This is really just a playback tool, but we definitely think that there's a wider use case for it. Overall, the project and its tool still in its infancy. I feel we're really only scratching the surface of what's possible with it. But the good thing is the project's already created a lot of enthusiasm and curiosity within the team, which for me really validates the decision to go with a JavaScript implementation. It's perhaps an unusual use case for JavaScript, but one that proves hopefully we can take familiar DX-friendly tooling and use it to solve unfamiliar problems that would typically be solved with low-level native code and would be out of the reach for front-end engineers. So thanks a lot for watching, and I am looking forward to the Q&A. Thank you.
An amazing talk. Thank you very much for delivering it as part of this year's event. I think I learned a lot about balancing video content on servers. I'm sure a lot of people do. You touched on at the end there the question I had written down while we're waiting for other people to put their questions in. Is this really something that's only applicable to video content delivery, or would you be able to suggest a few use cases for using your library that you've created outside of that?
Yeah, it's a really good question. So obviously the whole project was built with playback testing in mind, and there's a lot of features there that are quite video player centric. But any team building front end applications, especially single page applications, I think is probably already doing some kind of performance or network simulation testing, probably with Chrome DevTools at a minimum. What we can do with this tool is obviously introduce a much higher level of granularity there. So the internet isn't always like this linear thing in terms of what our applications experience. So if you're loading images from a certain CDN over here and videos from another CDN, the behavior of those two CDNs might be completely different. So it's not consistent. So being able to kind of create this sort of proxy layer and different behaviors depending on what content your application is downloading, I think has quite a broader set of applications. So yeah, as I said at the end, we haven't really started using that yet, but I could see the tool being extended, certainly with that in mind in the future.
Okay, so it sounds like it's something that's going to be carried on. You're going to carry on developing it, is that right?
Yeah, I mean it's still a work in progress at the moment as well. We kind of we're using it mostly in a kind of local development setting. We haven't quite realized the ambitions of running it at scale yet. So that's actually what we're working on at the moment is moving it to AWS and kind of getting the tests running in parallel.
Okay.
So that we can basically have it running in our CI pipelines, which is that was kind of from day one, that was the goal, and it took a lot of work just to kind of prove the concept and get to where we are before we can then actually put it into cloud infrastructure and hook it up to our pipelines.
So is it something that you'd be willing to take pull requests against, or is it not necessarily something for the open source world?
Yeah, I guess I should. So the link that I posted in the talk to GitHub is just like a small part of the whole tool. That's the basically the THROTTLE stream, which is kind of fairly agnostic. It's not playback specific. It's something you can install in a node.js server or a Dino server. Yeah. And basically use it to slow down traffic that's coming through. So quite general purpose. So that's open source. There's nothing really DAZN specific in there. The tool that I demoed in the video at the end is a kind of like internal playback testing stack, which has various different DAZN dependencies built into it. So not something that we would be open sourcing, but the idea I guess is that I'm trying to kind of show how somebody could use that THROTTLE and build a similar kind of tool out of it for different purposes.
Okay, and speaking of tools, you mentioned that you were using Dino as part of that stack. Have you got any thoughts on Dino? Do you think it's away from the prime time? Tell me your thoughts.
So it was back in May that I started. I've been following the Dino project for a long time with a lot of enthusiasm because I'm a massive TypeScript fan, and I continually get frustrated at some of the things in Node.js that we have to deal with. So I thought I'd kind of, just play around with it, and I realized it would actually be that this project would be a good use case for it, because we have this very simple little proxy server, and basically the initial prototype we had was using Node.js, and we had to leverage all sorts of libraries just to get the thing to work. We were using Express, and we were using various WebSocket libraries and things, and obviously we were writing in TypeScript, so we had a whole build system and everything. And then I looked at Dino and I realized we could do everything we needed completely out of the box without having to leverage any third-party modules. Don't need a build system, you just run it. It's TypeScript, it runs natively. And then on top of that, we had quite a lot of performance optimizations as well, but specifically because of the way that Dino handles streams under the hood, which is basically like a pull-based approach versus a push-based approach. So it's kind of waiting until the system is free before it processes, rather than just kind of letting you throw data at it, which is apparently a common performance bottleneck in Node, and something that the Dino team were trying to optimize for. So yeah, I love Dino. It wasn't the easiest learning curve, because when I started working on it back in May, I think it was still fairly experimental. Some of the stuff was unstable, and it still is to an extent, but and there wasn't a lot of like blog posts out there and things in terms of how to do X, Y, and Z. But yeah, it was rewarding. I would recommend it, especially on R&D projects like this. Maybe things that aren't customer facing, that fairly limited in scope. This was the perfect kind of application for it.
So I love that you said limited in scope there. Do you have any kind of idea of the amount of terabytes of video which is going through this piece of software?
So yeah, that's a good question. the little boxing video there that was in the presentation it's 5 minutes long. We've encoded it so that it matches the sports content that real DAZN customers see. So all the quality profiles match and so on. And just that 5 minutes of video is about 5 gigabytes when you take all the different quality levels and sum them all together. So if we're running thousands of tests many times a day in the pipeline, yeah, there will be many terabytes going through it. But yeah, we're using AWS to kind of make sure that's done in a performant way, and it's going through like multiple instances at once. So hopefully no bottlenecks there. But yeah, this is just a microcosm of what actually happens in our production video pipeline, which is obviously an order of magnitude bigger.
Yeah, I can imagine it's a very complex system. So we have actually had a question come in now. How frequently?
Yeah, I was worried the subject might be too niche to invite Q&A, but thank you, Philip.
Yeah, so Philip has put one in. How frequently do you plan to run testing in the pipeline, or on demand, or at set times?
So it kind of depends on the outcome of this parallelization work we're doing right now. We don't. We're going to be using something called AWS step functions with fan out. So basically what you saw in that little JSON test file was a test was 30 seconds long, and we want to have thousands of tests because there's all sorts of things that need to be tested which aren't right now. So the idea is that maybe within a minute or two you actually complete your whole test suite, even though each test is running in real time. So if that works correctly as planned, the whole thing should just take a minute or two. And in that case, we'll just run it on demand, basically. We have quite a nice CI pipeline. Most of the teams do it at DAZN. So devs are checking in. Every time a dev pushes code, it will run either the entire pipeline or a kind of small subset of the pipeline. So I think the goal would be to be running it there as long as it doesn't slow down pipelines too much. As I said, if we can parallelize it effectively, it shouldn't. But if we have some limitations there, or maybe cost limitations, and we want to set like a maximum number of instances, then in that case it might take a bit longer, and we'll think about moving it to nightly. But the goal was always to kind of make this like just a really unintrusive part of our developer workflow that people don't even have to think about. It's just something that's there, and just like any other testing tool that we use right now, that's the goal.
Ideal. That was a perfect answer. And with that, we're going to have to leave it there because the next talk will be starting very, very shortly. But I believe that people can come and meet the DAZN family on their sponsor stand, get their secret code for their free books. Will you be hanging for a little bit longer if anyone wants to come and find you?
Yeah, I'll be on Remo, probably in the DAZN lounge somewhere for a while. So yeah, drop me a message if anyone wants any more information.
Awesome. Patrick, thank you very much for your talk and for your Q&A session. It was really informative. See you soon.
Thanks, Tony.